Welcome to all of you to this session on evaluation control and its applications. My name is Jayanta Phadikar. I have been working in Wolfram Technology Group for about 2 years now. So in Wolfram language, every expression has a generic form. So it will have a head, then it will have elements, and each element will have subhead, sub-elements, and so on. So an expression looks something like this. So it is a bunch of heads and elements. So let's look at some examples. For example, this expression, as you can see, so this fits in with the generic expression here. And even simple looking expressions such as an assignment or a composite expression, so they can be represented in this generic form. And even graphics objects. They have the same form. So it has a head, it has elements, and then subhead, sub-elements, and so on. Now, Mathematica has a well-structured evaluation process, and it is kind of interesting and useful, but it is also a little difficult to understand. But if we want to appreciate the true potential of Wolfram language, it is good to understand this. So if we understand this, we can understand more sophisticated programming features such as delayed evaluation of set delayed, scoping abilities of plot table, etc. And we can also write enriched programs and custom functions and so on. So I'll be discussing these 3 topics. So the 6-step evaluation process, some application examples, and finally working with unevaluated expressions. So let's begin. So this is what happens when we type an expression and hit shift enter or shift return. So in the very beginning, Mathematica will evaluate the head of the expression. So for example, here we have this head. So Mathematica evaluates this to plus, and then it evaluates 30. Similarly here, so we have a list of functions, and our head, it takes the first element from this function. So it picks sign, and then it evaluates the result. And we can see the steps using trace. So as we can see, it evaluated this one first. It took out the first element, sign, and then it evaluated it. In the next step, for standard evaluation, it will evaluate all the elements in the order given. Or in non-standard evaluation, it will evaluate only selected elements. So let us see what I mean by this. So we have this expression here. So again, in the first step, it evaluated this variable, but here there is nothing to evaluate. But then it continued on evaluating each of these elements. So it evaluated print 5, then print 2, print 3. Similarly here, when we use plus, so it is, as you can see, it is evaluating the arguments in turn. Now in non-standard evaluation, Mathematica does not evaluate all the arguments, and let us see why this becomes important in certain cases. So for example, we have this plot function. If plot evaluates the arguments, then this becomes 4. So then Mathematica would just give a flat line like this, 2 squared. So that is not what we want. So that's why there are certain functions where the evaluations are not done for all the elements. For example, another example is table. So if we have a global variable x, table does not evaluate this argument. Otherwise, we just get 4 in all over the places. Similarly for the if statement, but I won't go through the details here for now. Okay, so we have these 3 attributes by which we can control which elements are to be evaluated. So this is how we can set attributes, see attributes, and clear attributes. So we can set attributes using set attributes. We can check the attributes using the attributes function. And using clear attributes, we can clear certain attributes. So with the hold first attribute, Mathematica would not evaluate the first element. So for example, we have x as 1, y as 2, z as 3, and we have set hold first for f1, and as you can see, it did not evaluate the first argument, but it evaluated the other arguments. With hold rest, it will evaluate all but the first element. As you can see here, it did not evaluate y and z, but it evaluated x. And with hold all, it won't evaluate any arguments. Now, in step 3, it will apply some transformations according to these 3 other attributes: orderless, listable, and flat. So let me go through these attributes briefly. So what orderless does is that it breaks the order of the arguments given by the user and rearranges the arguments, rearranges it as needed. So for example, we have this magnify image function which takes an image and it magnifies the image by a certain factor. Now, as you can understand, so this is our function, this is our image, original image. So now, we are using the function. The first argument is our image, the second argument is our factor, so this works as expected. But if we reverse the order here, it does not work, right? Because for the first argument, Mathematica expects an image. But if we set orderless attribute to the function, then it works in both ways. So the order of the attributes doesn't matter anymore. So that's what orderless does. So this is another example. So we have this function which expects the first argument to be a symbol, the second argument to be an integer, and the third argument to a real number. But as you can see here, it did not matter in which order we supplied the arguments. Although here in the definition we are specifying that we need symbol for the first one and so on. And there are some other examples. I won't go through those for now. So listable, I think most of you are familiar with. So what it does is that it distributes the definition over the elements. So as you can see here, we gave a list here and the definition got distributed to each element here. And listable is used for many built-in functions for a sign, for example, sign, log, and so on. So it is kind of convenient. So we supply a list and the listable attribute automatically distributes the function over the elements. And it does it for two-dimensional lists and so on. Flat, I won't go through the details. So basically here, the thing to note here is that certain functions, for example, plus times, they don't need these nested occurrences. So for example, this statement is equivalent to this one. We don't need this nested inner plus here. Similarly for times. So for such functions, we have this flat attribute which would just flatten these nested occurrences. And this does the same job as flatten function. This is a quick note about inheritance of attributes. The sections that I'm marking as optional, I won't go through those in details. You're welcome to take a look in your time. So let us say we have this function f1 which has the attribute hold all. Now as you can see, it is holding the attribute, holding the element here, it is not evaluating k. Now we set f2 equal to f1. Now if we evaluate this one, this holds the argument. Although the attribute of, we do not have the hold all attribute for f2. So this is a quick note, and it happens for all other attributes like orderless, flat, and so on. In step 4 and 5, Mathematica will apply the definitions. So custom definitions will be tried first before the built-in definition. So let us say we have this definition here, and so as you can see, Mathematica is first evaluating the arguments, then it is applying the definition. And the same holds for inbuilt definitions as well. And as I was telling, the custom definitions will be tried first. So for example, here we are modifying the sine function. We are telling that for sine of pi over 2, we need n1. And for the rest, sine should function as usual. So if we see the definitions associated with sine, as you can see, this definition is appended here, and Mathematica will try this one first before the general definition. Similarly for plus and so on. Okay, so there are situations where Mathematica can get into infinite loops, and if we know about the evaluation control, then we can understand it little better. So for example, this simple statement gets into an infinite loop. So what happens is that Mathematica will try to evaluate this right hand side first, then for x it will find this definition and it enters into that infinite recursion. So it keeps on finding this definition and it tries to substitute, so it goes into an infinite loop. And we have this recursion limit and iteration limit to control such infinite loops. Okay, so in the final step, so after applying the custom definitions, built-in definitions and so on, Mathematica will evaluate the result. So what I mean by this is that Mathematica will not leave anything unevaluated after it has applied all the steps. So for example, here we have the hold all attribute for sine. So as you can see, so it Mathematica, so in step 5 in step 5 Mathematica evaluated this one, and then in step 6 it just evaluated sine of 10. So yeah, I mean it is kind of a simple thing. So Mathematica will not leave anything unevaluated. Whatever it finds it after step 5, it will just evaluate it altogether. So this is an example where we are showing all the steps. So we have these 3 assignments and we are keeping this custom head which is equal to plus, and if we evaluate that, it simply does the summation. And as you can see, so the head is getting evaluated first, then the arguments are getting evaluated, then okay, I'm showing it here. Yeah, the head gets evaluated first, then the arguments get evaluated, and then the orderless attribute is applied, but we can't see it using trace. And then step 4 is not relevant because we do not have any custom definitions. And then finally Mathematica is evaluating the result. Okay, so let's look at some application examples where knowledge of evaluation control becomes important. So we need to hold an argument whenever we need to pass it symbolically or update it. So let's go to the examples directly. So this is a function for tracking a dynamic variables, the record points function. So what it does is that it takes a control object as the first argument and it takes an empty variable as the second argument, and whatever it will record all the points visited. So I am visiting all these points and this symbol will record all these points. So this is same thing with slider 2D. So let's say if we try to draw a circle here, so this variable should contain those points. Now we can apply a list plot on it to see the circle. Now the important thing to note here is that we need this hold rest attribute for this function. So let us see what happens if we do not have this hold rest attribute. Okay, so in the first case it should work fine. Okay, it works fine, but it does not work for any other subsequent runs. So what happens is that now this gets evaluated because we are not holding it. So then Mathematica sees a list of values. It does not see that empty variable. So this is an example where the hold attributes become important. Let's look at this one. A colleague of mine brought it to me a few days ago. It is kind of an interesting example. So let's say here we have a pure function just a table function, and we are feeding random integer to that. And as you can see, it is not creating unique random integers with this table. So what happens is that the pure function, it evaluates this argument first. So then it gets a random integer. So in this case, it was 0, and it is just creating the table out of those zeros. So to prevent that, we have to give this hold first attribute to the pure function. So in that way, so Mathematica is not evaluating it here. It is feeding it to the pure function. It is going to the table here, and then it is getting evaluated as usual. So we get a list of different integers. So this is an example with custom plot functions. So let's say we have this global variable x. Now we are trying to write a custom plot function that would generate a plot using lines and so on, lines and points and so on. And so it expects a function for the first argument, and it expects a range for the second argument. And this does not work. And that is because plot is evaluating this one. So it is saying 1000 instead of this function, and it is also evaluating this one. So we don't have the iterator anymore, we have the value. So to prevent that evaluation, we have to hold all the arguments. So we give this hold all attribute, and then the plot C works fine. And this is another example. I won't go through the details. Okay, let us look at some built-in functions. So table gets the scoping ability from the hold all attribute. So as you can see, this declaration of the global variable does not affect the operation of table, because table won't evaluate this one. It has the, as you can see, it has the hold all attribute. So if we remove that hold all attribute, so what we are doing is we are removing the hold all attribute, and we are giving it hold rest. So that means we are holding this argument. So as you can see here, table just gives, table evaluates this one, and basically it does not work without the hold all attribute. And the same thing happens for plot. Plot has the hold all attribute. Without the, if we remove the hold all attribute, it will just plot a single number. And so set delete becomes set without the hold all attribute. So here we have the set delete, and it works as expected. We are changing the value of x, and f is getting evaluated differently. But if we remove the hold all attribute of set delete, then it behaves just like set. So it does not perform that delayed evaluation anymore. Oops, sorry, I think. Yeah, so it does not do that delayed evaluation anymore. Okay, so in some cases we have to override those hold star attributes of the built-in functions. So here are a couple of ways to do it. So method one is that we can wrap evaluate around that argument, so it will force the evaluation. So here, let's say we have this function with hold all attribute, and as you can see here, it is not evaluating the argument. But if we wrap evaluate around it, then it evaluates. Now we can do that using replace all. Here is a technique with the with function which can do it, and this is known as injector pattern. It is kind of reversed replace all. I'll not go through the details of how it works for now. And let's look at some examples where we can apply these methods where we have to apply these methods. So this is an expression, and let's say we want to, okay, let me clear the variable. So this is an expression, and let's say we want to use this expression inside function. So, but this does not work, as you can see. This is because the pure function, it has the hold all attribute, so it won't evaluate this variable to this one. So Mathematica is not seeing this one here. So if we wrap evaluate around it, then it works as expected. For the sake of time, let me skip this one. Let me show this one. So let's say we want to pass a pre-constructed list of options. So let us say for the plot function, we want to set plot points, max recursion, and plot style. And we want to create a list first and then pass it to the plot function. And this does not work because plot has the hold all attribute. And similarly for other functions like n-integrate, if we create a list of options and try to pass it, it does not work. But if we wrap evaluate around those, then it works fine. Okay, something went wrong, sorry. Okay, this does not work and sorry, here you mean? Here? Here you mean? Okay, let's check. Okay, it does not work as well. So basically, I think it is not evaluating this one at all. So yeah, it is not seeing the options. All right, let me skip the other examples for now. Let's go to the unevaluated expressions. So these are some functions that can prevent evaluation. For example, if we wrap hold around an expression, it does not evaluate. Similarly, with hold form, we have unevaluated. So this is an interesting function. Let me explain this. So yeah, unevaluated does the same thing as hold, but what it does is that it the head here Mathematica still sees the head as plus, not unevaluated. So what I mean is that let us say if we have hold here. So in that case, Mathematica sees the head hold, but here it sees the head plus. So that becomes useful in certain cases. We'll go to the example soon. So similarly, we have differ. Basically here it does not evaluate the expression, but if we can copy and paste it, and then it works as the original expression. Similarly, we have inactivate, which inactivates the heads. Now let's look at some examples where unevaluated expressions can be helpful. So we can find the length of an expression using the unevaluated. So if we try to do, let us say, length of 1 plus 2 plus 3, then it just returns 0. That is because Mathematica evaluates this one and then tries to apply the length. So it is evaluating this one to 6 and then it tries to apply the length function. But we can get away with it using the unevaluated function. Similarly, we can find the length of a variable name. So we need this unevaluated function because otherwise Mathematica will evaluate this one. So let's say if we have if we do not have the unevaluated, then Mathematica okay, so then Mathematica converted this 100 to string and then it returns the length of the string. Okay, I don't know why I can't expand it. Let me go to working mode. So we can extract specific parts from an expression. For example, here we are selecting the real numbers using cases, and we need again unevaluated here because otherwise Mathematica will simply evaluate this expression. And similarly, we can find the integers and so on. Okay, so we'll end with this Strauss-Krzyzewski's technique. So this was invented by one of our developers. So what it does is that it can do in-place evaluation at an arbitrary depth. So let's say we have this function and let's say we want to evaluate only this term. Now we can't use evaluate here because evaluate does not work at an arbitrary depth. If we wrap evaluate around the whole thing, then it will just evaluate the entire expression. We can use some of the earlier methods like with or injector pattern, but as you can see, these are kind of invasive because we are kind of meddling with the original expression, like we are substituting x here, we are substituting x here, and so on. So what this does is that, so this is the technique, so it uses the width similar to the injector pattern, but it kind of forces that evaluation using this condition. So, okay. Yeah, so it forces that evaluation. And similarly, so we can apply it to in different cases. For example, here we have this function and we want to apply this function only to this third term. So we can do it using the technique, and similarly here we are applying that function to only real numbers. So we have set up the pattern and rest is the technique, and it evaluates fine. So this is a little more elaborate example. So we have a binomial expansion here, and what we are doing is that we are trying to evaluate only the odd terms. So we have substituted some values for a and b, and we are picking out the odd terms using odd q, and we are applying the technique to evaluate only the odd terms. Okay, so yeah, that concludes my presentation. Thank you for your attention, and if you have any further comments and questions, we can set up some time and you can send me a message through Pathable. All right, thank you.